Welcome back to section 9.2, Angles and Radian Measure. In our previous lesson, we were talking about angles and standard position, and we were introduced to radian measures. There's great advantage to using radian as opposed to degrees when we start graphing curves. We'll get into that in a future section. Today's lesson won't be all that long. We're going to focus in on arc length and area of a sector.
In day one's tutorial, we were trying to find coterminal angles in degrees, and we were doing so by taking measures of angles and adding 360 or subtracting 360 in order to get different angles that are going to end in the same location, so that means coterminal. And typically we want one that's positive and one that's negative. I wanted to just give an example with radians before we jump on to other material today. So if we start off with 7 pi over 6, what's another angle in radians that's coterminal with that? Well, what we want to do is add another revolution. In radians, that's 2 pi. So if we have 7 pi over 6, 2 pi with a common denominator would be 12 pi over 6. So when we add those together, we come to 19 pi over 6. It's the same idea if we want to go negative. We just simply subtract 2 pi, which would be 12 pi over 6. And when we do that, we come to negative 5 pi over 6. If our angle is negative 3 pi over 10 and we want to find something positive, we can add 2 pi, but finding a common denominator gives us 20 pi over 10. Same thing if we want to subtract. Therefore, it's just a matter of adding and subtracting and seeing what comes about. If we have something like 2.4 radians, you know that that's not degrees because the degree symbol is missing. We still want to either add or subtract 2 pi. Now, we just take the 2.4 and we add 2 pi to that. Pi, remember, is an irrational number, so it's an approximation, but it's about 2.683. And if we go to subtract, it's negative 3.883. So same concept, adding or subtracting a full revolution. In degrees, that would be 360 degrees. In radians, it would be 2 pi. If that requires finding a common denominator, so be it. Not too hard. The main crux of our lesson today is to work on finding arc length and also area of sectors. Remember, a sector is a region of a circle that's bounded by 2 radii and an arc of the circle. The central angle theta of a sector is formed by the 2 radii. So in other words, the vertex has to be at the center of the circle. So before we go finding the arc length or the area of the sector, it might be helpful for us to remember what's the circumference of the circle and what's the area of the circle. And remember, the key word here is fraction. The arc length is just a fraction of the circumference, and the area of the sector is just a fraction of the circle. So one of our formulas, circumference, is 2 pi r, or pi times the diameter. If our radius in this circle is 5, then the circle is 2 pi times 5, so 10 pi. The area of our circle is pi r squared. If the radius is 5, then our area is 25 pi. So how do we find the arc length? Well, the arc length is just a fraction. Read the sentence. The arc length, so AB, equals just a fraction. We'll talk about that fraction in just a second, of the circumference, so C. The fraction is the central angle 60 degrees divided by the full circle 360 degrees. So we get 1/6 times the circumference. The circumference was 10 pi. And so our answer is 5 pi over 3. If we want to know the area of the sector, that shaded region up in that circle, it's basically the same formula. The area is the fraction times the circle. It's the same fraction. It's the central angle 60 degrees divided by 360 times the area. That reduces to 1/6 times 25 pi, and so it comes to 25 pi over 6. We can find decimal approximations, but the idea is to keep in mind if we know the formulas for circumference and area, we just multiply by the fraction of the central angle over 360 to get our results.
This is another representation of the same problem we just did, so when we find the arc length and the area of the sector, our answer should be the same as before. The only difference is the representation of the angle. It was 60 degrees and now we're referring to it as pi over 3 in radians. But the formula is basically the same thing. We're going to take that central angle and divide it by the full circle's measure, which would be 2 pi, and multiply it times the circumference. But in this formula, notice that we have 2 pi in the denominator and also as part of the circumference. Those simplify out, so we get the angle pi over 3 times simply the radius 5, and so that becomes 5 pi over 3. That's the same answer as before. And in general, the arc length of a sector is going to be the central angle in radian measure times the radius. Take that idea over to the area, and our area is going to be the fraction of the area of the full circle. The fraction is pi over 3 divided by 2 pi. We don't quite lose the full denominator there in purple, but the pi's cancel out, and we have pi over 3 divided by 2 times the radius squared. Or it's 1/2 the angle times the radius squared. When we simplify that down, we'll get 25 pi over 6. That's the same answer as before. And if you just look 2 lines above, in general, if we know our angle in radian measure and the radius, then the area of that sector is 1/2 the angle times the radius squared. So the key takeaway from day 2 of section 9.2 is that if we are given radian measure, then we can say that the arc length is the radius times that angle given in radian measure, and the area is 1/2 the radius squared times that angle. When officials set up a sector for the shot put or the discus or the javelin in track and field, they have to estimate how far someone can possibly throw those implements and go out that radius, or go out further than that radius, so that they'll land within the sector. And they create that arc, as you can see up at the top of the picture, as the landing area. They presume that people won't be able to throw further than that. Well, in this example, they've gone out a radius of 22 meters, and they've set the angle at pi over 6. So the question is, how long is that arc length, and also, what's the area of that sector? So given the fact that we have an angle in radian measures, we can use that simplified formula. It's just simply the radius times the angle, 22 meters times pi over 6. That estimates out to being about 11.52 meters long. What about the area? The area is 1/2 the radius squared times theta. We simply plug in the values and come to our approximate answer. Here's our exact answer, 484 pi over 12, and then that estimates to being about 126.7 meters squared. So this was a comparatively short lesson in relation to day 1, but it seemed like too much material to squeeze into one single tutorial. We looked at angles in standard position, and we converted from radians to degrees and degrees to radians. And today we were looking at arc length and area of a sector. If you have any questions, please reach out to us. Thank you very much for watching. Have a great day.